So as we see, the type of the signal selected for the discussion is sinusoidal. I hope you remember the sine type or the cosine type. So these are especially the sinusoidal signals, which are basically of periodic nature. So periodic nature means a same structure of one wave cycle is going to repeat onto the time axis. As the time progresses, the same amplitude changes we observe. So that is what the periodic signal, and this is the sinusoidal signal. Either you talk about the sine or the cosine, we can have double-sided, single-sided here. Now the point of discussion here is spectral analysis of such sinusoidal signal. So for example, if I talk about the sine wave, as you see in this illustration in the upper half, there it is a plot of amplitude values versus the time values. So here it is basically the signal which is of the frequency 1 kilohertz, and the representation is made in the time domain. So on the horizontal axis we have measurement of time in terms of millisecond values, whereas on the vertical axis we have markings of the amplitude levels. Now when the same kind of the signal information, that is 1 kilohertz signal, is represented by using the frequency domain. So here in this graphical plot, on the horizontal axis instead of the time, we have the markings of frequency in terms of hertz, and again the amplitude level on the vertical axis. Now you see the visualization compared for both the plots. The signal is the same, that is 1 kilohertz signal here, but as the representations are into the different domain, the visualization or the nature of the graph seems to be different here. So in the time domain, it is evident that there it is a repetition of the same structure as we go on with the progress of the time parameter, but that is not the case into the frequency domain, as we have frequency marking. So we see a single frequency component. So these are just the ways of representation of the signal information into the different domains, and as per the convenience for analyzing the signal with the application at hand, we shall be selecting that particular representation here. So there are a lot of applications where there it is a requirement of determining into the discrete time domain the frequency contents of a continuous time signal, and this particular procedure is mostly known as simply the spectral analysis. Now this particularly involves either the determination of energy spectrum or that of the power spectrum for the corresponding signal here. Now the spectral analysis methodologies are having a little bit of observation I will try to discuss with you people. If for example we have a continuous type of signal, generally we have been denoting it by f of t or g of t here. So to get the signal processing techniques performed over it, as we have discussed in this particular subject, we need to get the continuous time signal representation into the discrete time equivalent representation. So for f of t we have made f of n, for g of t we have made g of n, and this particular representation should provide a good estimate of the spectral properties of the time domain representation of the signal, of course the continuous time domain representation. But in most of the cases, this time domain representation, continuous type, is defined for, see, the range, the time parameter from minus infinity to plus infinity, and equivalently for the discrete time representation also, the discrete time parameter small n will be ranging from minus infinity to plus infinity, and for this wide range it is quite difficult to have evaluation of the spectral parameters of an infinite length signal. Now here for the discussion purpose we are going to have consideration of Fourier analysis of a stationary signal composed of sinusoidal components here. So here we assume that the parameters those characterize the sinusoidal components as like the amplitudes, frequency and phase, they are not changing with the time. So that is why we are talking about the stationarity of the signal for the sinusoidal type here. So for such a signal, in general, if you are carrying forward the representation g of n for discrete time domain, the Fourier analysis can be carried out by computing corresponding Fourier transformation. So the forward type of the Fourier transformation, the mathematical formulation can be expressed here. The transformed version for small g of n can be denoted by capital G of e to the power j omega, that is expressed in terms of the summation with the index variable n is equal to minus infinity to plus infinity for the discrete time domain representation g of n multiplied by e to the power minus j omega n. So if initially g of n, small g of n, is assumed to be infinite length sequence, so to make it a finite length sequence, it is first of all windowed by having a multiplication of it with n length window. Let us say in general the window we denote by w of n. So this way we first of all get it into a finite length sequence. We can have another notation as like gamma of n, that is equal to the product of the initial infinite length sequence g of n with the window signal here for a finite length here. So the spectral characteristics of the windowed finite length sequence can be obtained by again performing the Fourier transformation. So the same mathematical formulation as we have here, the equivalent form we can have for such finite length sequence here, making the changes to the limits of this particular summation. So then it is assumed to provide a reasonable estimate of the Fourier transform. Here we have capital G of e to the power j omega of the discrete time signal g of n. Now such a Fourier transform version of the windowed finite length sequence is further evaluated as a set of capital R discrete angular frequencies equally spaced into the range 0 to 2 pi for the angular frequency omega by computing its R point discrete Fourier transform, that is DFT. So this DFT can be denoted as capital gamma of k. So for providing a sufficient resolution, the DFT length capital R is selected to be greater than that of the window length that we generally denote by capital N, and this is to be done by zero padding the windowed sequence with R minus n zero valued samples here. And the methodology for carrying out the discrete Fourier transformation is usually the FFT algorithm. So in order to evaluate this particular methodology, whether there are any limitations or not, so here we are trying to analyze the effects of windowing first of all before application of the forward Fourier transformation, and the evaluation of the frequency samples of the Fourier transform via discrete Fourier transform, that is DFT methodology. So before making interpretation of the spectral contents of the signal, first of all let us have examination of the relations between the transforms and corresponding frequencies. So let us have the relationship between the R point DFT and corresponding Fourier transform analyzed. So for that purpose we have the mathematical expression. So here capital gamma of k that we see on the left hand side is the R point discrete Fourier transform DFT here, whereas we have capital gamma of e to the power j omega, simply the corresponding Fourier transform. So that we see at the right hand side. So capital gamma of e to the power j omega, whereas we have omega is equal to 2 pi k divided by r, provided small k is greater than or equal to 0 but less than or equal to capital R minus 1. Now the normalized discrete time angular frequency that can be denoted by omega suffix k, that corresponds to the DFT variable that is denoted by small k, here we express as omega suffix k, that is equal to 2 pi k divided by capital R. Similarly, the continuous time angular frequency can be denoted by capital gamma suffix k that corresponds to the DFT variable or the index number denoted by small k. So here we express capital gamma suffix k is equal to 2 pi k, the numerator will be the same, divided by r into t. In the earlier expression, in the denominator there should not be any t here, that is a typo mistake. So here it should be r only. So for making the interpretation of the results of DFT based spectral analysis at the correct form, let us have consideration of the frequency domain analysis of the sinusoidal signal. So sinusoidal signal, or in the discrete time domain you call it a sequence here. So infinite length sinusoidal sequence that we had denoted or considered initially to be g of n. In the first equation you see it on the right hand side here. So let us have that g of n to be normalized by the angular frequency omega suffix 0. So that is expressed as, here we have g of n that is equal to cosine of omega suffix 0 into n added by phi. Now by expressing the sequence as g of n is equal to 1 by 2 times, in the bracket we have e to the power j times omega suffix 0 n plus phi, which is added by e to the power minus j times omega suffix 0 n plus phi. Here the substitution we have made for the cosine by the Euler's formula. So we arrive at the expression for corresponding Fourier transformation by using these notations as capital G of e to the power j omega equal to pi as a constant outside the summation operation, where the index variable L ranges from minus infinity to plus infinity for the addition of two terms. So here we have the first term inside the bracket e to the power j pi in multiplication to del of omega minus omega 0 added by 2 pi L, whereas the second term is e to the power minus j pi del of omega plus omega 0 added by 2 pi L. The term is added to earlier term. So therefore the Fourier transform, we see a periodic function of the angular frequency omega with the time period of 2 pi. So it will be containing the two impulses as we see corresponding to the two terms in each of the period. If the frequency range minus pi to pi for omega it is there, so the impulse will be at omega is equal to omega 0 of the complex amplitude pi into e to the power j pi, and impulse will be at omega is equal to minus omega 0 of the complex amplitude pi into e to the power minus j pi. Now to analyze g of n into the spectral domain using the DFT, discrete Fourier transform, let us employ a finite length version of the sequence that can be expressed as small gamma of n that is equal to cosine of omega 0 n added by pi, where small n is greater than or equal to 0 but less than or equal to capital N minus 1. The computation of the discrete Fourier transform of the finite length sinusoid can be considered here. So the example can involve the computation of the discrete Fourier transform of length, let us say for example 32 sinusoid with a certain frequency. Next to that we can again have a computation of 32 point discrete Fourier transform of the length 32 sinusoid with little bit variation into the frequency value. The phenomenon of the spread of energy from a single frequency to many DFT frequency locations is also called as a leakage. So for better understanding, let us see the illustration of Fourier transformation of a sinusoidal signals that is windowed by a rectangular window. So here you see the illustration. On the horizontal axis we have normalized frequency values. We can see the markings 0, 0.5 pi, pi, 1.5 pi, then 2 pi. Whereas on the vertical axis we can see DTFT magnitude here. To better understand the shape of the Fourier transformation as we see in this particular illustration. The two major lobes here, peaks here. Let us have observation that the sequence that we have shown with the help of earlier expression small gamma is windowed version of the infinite length sequence small g of n that can be obtained using a rectangular window w of n here. So let us define this particular window w of n that opts the value 1 when we have small n greater than or equal to 0 but less than or equal to capital N minus 1. Elsewhere the value of this window is equal to 0. So there is no span of this particular window. So therefore the Fourier transformation of small gamma of n can be given by the frequency domain convolution of the Fourier transform of small g of n with the Fourier transform of the rectangular window. So here we have capital gamma of e to the power j omega, that is the Fourier transform of small gamma of n, the last equation that you have seen on the previous slide, that is given by the frequency domain convolution as we have discussed. So here we have psi suffix r of e to the power j omega that we have seen on the RHS of the earlier equation expressed as here. So capital gamma of e to the power j omega is given by 1 upon 2 pi integration minus pi to plus pi, or capital G of e to the power j phi multiplied to psi suffix r of e to the power j times omega minus pi d phi here, whereas we have psi suffix r of e to the power j omega equal to e to the power minus j omega in the bracket capital N minus 1 divided by 2 multiplied to the ratio of sine of omega capital N by 2 divided by sine of omega by 2. So making the substitution of capital G of e to the power j omega, let us obtain capital gamma of e to the power j omega equal to 1 by 2 into e to the power j phi psi suffix r of e to the power j times omega minus omega 0, which is further added to 1 by 2 times e to the power minus j phi multiplied to psi suffix r of e to the power j times omega plus omega 0. So here it can be noticed that the Fourier transform as we see in this expression, which is for the windowed sequence small gamma of n, is the sum of the frequency shifted and amplitude scaled Fourier transform of the window in general w of n with the amount of frequency shifts given by plus minus omega 0. So in this discussion, if we introduce one more sinusoid here, so it will definitely bring more complexity here for the signal being analyzed here. So in this regard, for having the DFT based spectral analysis completed here, there should be the examination of effects onto the DFT length on the spectral analysis. Also, there should be a study of effect of the spectral separation on the DFT of the sum of two sinusoids because of one more sinusoid, and there should be the study of minimization of the leakage using the tapered window here. So such type of the complex applications of the signal processing domain as is the spectral analysis of sinusoidal signals is of course possible, but with little bit of increase into the computational complexity here. So this was the brief introduction to the spectral analysis of sinusoidal signals.